Welcome to part 2 of our VisRad Introductory series. In this video, we're going to start building our target component system in the VisRad Target Viewer. The build process for this target system will be broken up over the next several videos in this series. Now, before we start the build process, let's take a quick look at the target system we'll be building. If you have a history with inertial fusion experiments, I'm sure you'll recognize this setup. But for those of you who are new, this center chamber we see here is what's known as a Hall realm. Hall realms are a common structure used in inertial fusion and high energy density physics experiments. Their purpose is to essentially convert laser energy into X-rays, which will indirectly heat the contents of the Hall realm. Now, to highlight a few things, let's switch over to the solid frame view. That's the third viewing option over here to the right. This will just make all of our wireframes nice and solid and opaque. So when we look at this target system, we can see this wire jutting out with this disc connected to the wire, which is aimed at some kind of square and a hole. So what's going on here? Well, the square packet we see here is actually our material sample of interest. This is what our Hall realm is set up to heat. The disk in front of our sample material is the backlighter, which will also be heated by lasers to produce X-rays. These X-rays will hit our heated sample and then can be observed through this diagnostic hole on the other side of the Hall realm. This would let experimentalists get different optical information on our sample material. The key thing to notice here is that the diagnostic hole, our sample material, and the backlighter all need to line up along a single line of sight. We can also see two washer-like structures on the inside of our Hall realm. These are basically just shields set up to help guarantee whatever signal reaches our diagnostic hole is coming from our sample and not elsewhere in the chamber or elsewhere in the Hall realm. Finally, we see a long cylinder connecting to our Hall realm. This cylinder is what's referred to as a stalk. Stalks are actually a fairly important component to designing a VisRad target system, and the topic of adding a stalk will be its own video later on. Now that we've gone over the end goal of our target system, it's time to open a fresh VisRad workspace, and we'll start the build process. With our fresh VisRad workspace, we'll need to select a target chamber. And for us, that's the Omega chamber. So let's start out with adding our Hall realm. Luckily for us, if we go to Target, Add Object, we can see cylindrical Hall realms are a primitive object that we can actually start with. After selecting the cylindrical Hall realm, the Object Parameters dialog will pop up. This is where we'll set our sizing and positioning information for our Hall realm. First, let's go ahead and change our target object name to just Hall realm. And we can see that the first tab that our dialog opens to is the Position tab. This is where we'll set our object's position in the chamber as well as its orientation. For now, let's leave the default values here and come back to them in a moment. Let's go to the Size and Gridding tab. This second tab is where we can set up the dimensions of our Hall realm. For this example, we'll be using a radius of 0.8, a length of 1.6, an LEH radius of 0.6, and an R corner of 0.1. These will basically just set our shaping parameters of our Hall realm to be a nice basic Hall realm shape for what we want. If we want to add more resolution to our object, we can choose to add more grid points over here to the right, but for now, the resolution here is totally fine. If we click the Apply button and move our dialog a little bit, we can see our basic Hall realm appear in the target chamber viewer. Now that we have a properly shaped hole round, we can worry about its orientation. Let's click back to the first tab, the Position tab, and now we'll need to choose a reference coordinate system. We have three options to choose from to define our reference coordinate system. The first one is the target chamber or mount. We can basically use the reference coordinate system of the target chamber or some preset mounting ports. The second option is the target component option. This would be a drop-down of all the different target components. So we could use the reference system of, say, some cube up here to the right. We don't have any other target components in our system, so this is grayed out. And finally, the third option is the option to use a port-aligned coordinate system. Port refers to the diagnostic ports set up within a facility. Much like lasers, VisRad comes with these ports already modeled and set up. To see a list of these ports, we can go to View and then select the Port Positions dialog. This will give you the orientation of each port relative to the chamber, as well as their assignment at the facility. If you would like a visual, you can also open the port viewer and see how all these ports are laid out. For us, we'll go ahead and choose to align our hole round with port P6. To see the line of sight of this port, we can actually toggle it on and off over here with the Show Line of Sight option. You can see it pop up in the chamber behind us. I'll move this so we can see a little better. And now we want to adjust the orientation of our hole round so it lines up with this line of sight. I'll close this and go back to our hole round object information. And we have two options here. We can go to the port axis and choose P6. But also it's good to note that port P6 corresponds to TIM4, which is also in our first mounting reference coordinate system. So you can really use either. I'll just use the port P6 option over here because I'll refer to this as P6 quite a bit coming up. So now if we hit apply, we can see our hole round lines up perfectly with the port P6 line of sight. The rest of the information in this object parameters dialog don't really need to be altered for us. This center section sets the centroid of our hole round, and we're okay with that being at the 000 point of our target chamber. And the third section down here sets the orientation angle offset. We're already lined up with port P6, but if we want to deviate from that a little bit, we could rotate away from the default port P6 using these guys. But for us, we can just set them all to 0 because we're already lined up with port P6. And with that, our basic hole round is basically all done. Since we were just looking at ports and line of sights, let's go ahead and set up our line of sight for the diagnostic hole, square sample material, and backlighter lineup that we just talked about. We'll go ahead and reopen the port positions. And for this setup, we want all three objects to line up with port H14 for our example. So we'll go ahead and turn on this line of sight as well. This will be the line of sight leading directly into the side of our hole round. I'll go ahead and close this guy again. And now we can add the easiest of these three features, the backlighter. To do this, we'll go to Target, Add Object, and we're going to use a disk as a backlighter. We'll label this as backlighter. And now we'll go to the size and grading tab and give this backlighter a radius of 0.5. Now, how do we line this backlighter up with our new line of sight? Well, let's go back to the position tab and we can choose port H14 from our list of ports for our reference coordinate system. Just double click it. We can hit apply and we can see a disk appear at the center of our hull realm. And we want to shift this guy a little bit down. So I'll set this to a Z value of negative 3.5, hit apply. And now we can see our backlighter is set down our H14 line of sight. And now we can go ahead and add our shields. To do that, we can just go to Target, Add Object, and choose a disk. I'll name this disk shield underscore top. And we'll want to be in the reference coordinate system of our hull realm. And we're going to be using cylindrical coordinates again. And now we want to position the shield right at the top of our material sample, which will have a height of 0.8 millimeters. So I'm going to set our Z to 0.4 millimeters. If I hit apply, we can see our top shield appear in the target viewer. Now it's looking a little low resolution along the edges. So what I'll do is I'll actually just increase the grid points to 30. Hit apply, and we can see it smooths out much more into a clean disk. And while I'm at it, I'll just go ahead and adjust the hull realm to 30 grid points in the azimuthal as well. And you can see this smooth out as I do it. And now for shaping the disk, we will set the outer radius to 0.8 millimeters, which is the radius of our hull realm. For an inner radius, we'll just use 0.5 millimeters, and we'll use a wall thickness of 0.01. And there's our top shield. For the bottom shield, we could just redo all of this, but instead we can just right-click on the top shield, say duplicate, edit the duplication, and change its name to bottom shield. And we'll just set the Z to negative 0.4, which will be the bottom of our material sample. And with that, both of our shields are now in place. And now to end the video, I want to go over a few key things to remember when you're constructing target components. Let's say I wanted to move our hull realm up in Z in the reference system of our target chamber, but maintain its P6 orientation. Well, if I were to just switch to the reference coordinate system of our target chamber and hit apply, you see our hull realm readjust itself to line up with the target chamber, and we don't want that. Let me just go back to P6 quick to go back to what we were at. Now, how do I move this in the reference coordinate system of the target chamber while maintaining its orientation? Well, there's this little checkbox down here, automatically update position/orientation angles when changing coordinate system parameters. Now, if I switch to the reference coordinate system of the target chamber, we can see the orientation angles automatically adjust to maintain the target component's orientation through the reference coordinate system change. Now I can move the hull realm up in Z or anywhere I want in the chamber. But notice when I move the hull realm, the backlighter didn't move with it. Well, if I look at the object parameters of the backlighter, we can see we're in the reference coordinate system of port H14. If you want to check all of these all at once, you can just go to Target, Show Reference Coordinate System Tree to see all of your target components references. And here we can see the shields are in the reference coordinate system of the hull realm, which is referencing the target chamber, but our backlighter is in a completely different branch, referencing port H14. So if I open the object parameters of our backlighter, make sure our automatic update checkbox is on, and switch to the reference coordinate system of our whole realm and say OK, we can look at our tree and we can see now all of our target components are in the same branch. The backlighter and shields are referencing the whole realm, which references the target chamber. And that means if I move the whole realm, the shields and backlighter will move with it. And indeed, if I move our whole realm up in Z in the target chamber, the backlighter moved with it. And with that, we're at the end of this section of the video. In the next section, I'll be going over how to clip out segments of our whole realm to add our diagnostic hole and material sample. So I hope to see you in the next video.